Well, how are you doing, Linus? I hope you are doing well. Today, I want us to look at this grade 11 topic, which is global air circulation. Then what is it that we are going to cover in this topic? We are going to discuss in details global air circulation. Firstly, we are going to look at what is global air circulation. Then secondly, we are going to discuss the world pressure belts. Then thirdly, we are going to look at pressure gradient force and the impact it has on the way that the wind is flowing in our planet. Then we're also going to discuss about Coriolis force. And lastly, we are going to discuss about geostrophic flow. Let's start by looking at the definition of global air circulation. What is global air circulation? What you need to understand is global air circulation is the large-scale movement of air across latitudes in response to the unequal heating of the atmosphere. Since the atmosphere is heated unevenly, that is why we have global air circulation. That is why we have this large-scale movement of global air circulation. Let's start by looking at pressure belts. What you need to know, learners, is that we have high pressure belts and low pressure belts. So in this section, we are going to discuss how are the low pressure belts formed and how are the high pressure belts formed. Air pressure is not uniform over the Earth's surface. The global air circulation then produces three pressure belts because the pressure is not uniform over the Earth's surface. The first pressure belt is the equatorial low. Where do we get the equatorial low? We get it in the equator. The equatorial low, high temperature zone, low pressure, that spans the equator. It's also known as the intertropical convergence zone, or you can say the ITCZ. It's located where? In the equator. Then we have the subtropical high pressure belt. The subtropical high pressure belt, this one we have moderate temperature. A high pressure reaches near the margins of the tropicals or mid-latitudes. The subtropical high, it's a high pressure belt. Then lastly, we have the subpolar low. The subpolar low, it's a low pressure belt. The cold, low pressure zones near the margins of the polar circles. Then if we have a look at this diagram, we can see where these pressure belts located. The subtropical high is found 30 degrees north and south. The subpolar low, we get it, is located in the 60 degrees north and south. Then we also have the equatorial low pressure belt, which is also known as the intertropical convergence zone, which is located in the equator at a latitude of 0 degrees. Then it's key to know where they are located as well. If you can note in this diagram, you can see that across both hemispheres, there are 5 pressure belts. Then let's discuss this now. How are the low pressure belts formed? Remember, when we have warm air, it's lighter. So warm air is rising. Warm air, it's rising. And from what? And from your low pressure belts areas. Then when we have cold air is dense, it's heavy, it sinks or descends, and then it forms what? It forms the high pressure belts. Then, if we can just have a look, since we have the pressure belts, The force that acts between the pressure belts is pressure gradient force. Pressure gradient force is the force that acts between high pressure belt and low pressure belt. And then air flows as wind along the pressure gradients from high to low, but it follows a curved path. We are going to discuss why does it follows a curved path. Then if you can note, in the intertropical convergence zone, wind from both hemispheres meets or converges at the intertropical convergence zone in the equatorial low. That's whereby wind from both hemispheres converges or meets. Then what is key to understand in terms of the pressure belts is that pressure belts, they shift with the seasons. As the seasons changes, they also shift with the seasons. As the seasons change during a year, the sun moves overhead between the tropical of Capricorn and the Tropic of Cancer. Then this means that the positions of the pressure belts shifts or migrates south or north of the equator. So you must know, learners, that pressure belts, they shift with seasons. Now let's discuss pressure gradients. Pressure gradients. Pressure gradient is the rate of change of atmospheric pressure. Then when we talk about pressure gradient, you must know that we are referring to the rate of change of atmospheric pressure with regards to horizontal distance at a given point in time. That is your pressure gradient. Or we can put it simply in this way. Your pressure gradient is the force that causes air to flow from a high pressure to a low pressure. Remember when we were discussing the pressure belts, I said we have the pressure gradient force that acts between your high pressure belt and your low pressure belt. So the pressure gradient force is that force that causes the air to flow from high pressure to a low pressure. Pressure gradient affects the speed of wind. Pressure gradient affect the speed of wind, which means the speed of wind, it depends on the pressure gradient. Big differences in atmospheric pressure will result in stronger winds. So if we have big difference in atmospheric pressure, it means that we are going to have steep pressure gradient. And if we have steep pressure gradient, that will then result in strong winds. Then if we have small differences in atmospheric pressure, that will result in weak pressure gradient. And if we have weak pressure gradient, it will result in gently winds. If you understand this, then you will be able to understand how the wind flows and what affects the speed and how strong the wind is. Pressure is indicated on synoptic weather maps by lines called isobars. Don't forget that. Remember that isobars, they indicate the atmospheric pressure. Isobars on synoptic weather maps are not equally far apart. You have to understand this about isobars. And that is when the isobars are close together, we are going to have steep pressure gradient. And steep pressure gradient produces strong winds. Then when the isobars are far apart, we are going to have weak pressure gradient. And then when we have weak pressure gradient, it results in gently winds. Then the pressure gradient is always at right angles to the isobars. And then the wind blow diagonally to the isobars. But let us have a look at this diagram, which clarifies what I've just explained now. If you can note, we can see when we have shallow pressure gradient or weak pressure gradient, when the isobars are far apart, then it will result in low wind speed. But when the isobars are close together, it means that we have steep pressure gradient. And then when we have steep pressure gradient, it will result in high wind speed. It will result in strong winds. That is key to understand about pressure gradient. If we have a look at this synoptic weather map, you can see the isobars where they are closely together, we have a steep pressure gradient, which results in high wind speed and strong winds. Then if you have a look here, inland we have the isobars that are far apart, which results in what? In weak pressure gradient, which also results in low wind speed. So you must understand that when the isobars are closely together, we have steep pressure gradient, we are going to have a high wind speed and strong winds. But when they are far apart, we have weak pressure gradient and we are going to have a low wind speed. The wind is not going to be strong because of the weak pressure gradient. We have discussed almost everything about pressure gradient, but please learners, don't forget, pressure gradient force is responsible for making the air flow from your high pressure area to low pressure. Then now we are going to look at Coriolis force. Coriolis force, the earth rotates on its own axis from west to east at different speeds. Earth rotational speed is fastest at the equator and slowest at the poles. Then the rotation of the earth and the speed at which it rotates, it creates a force called the Coriolis force. You must know that the force, which we call it Coriolis force, we have it because it's caused by the earth rotation. The Coriolis force, it is caused by the fact that the earth is rotating. The stronger the wind speed, the stronger the Coriolis force. Then the Coriolis force effect is zero at the equator, which means that the equator is zero. We don't have Coriolis force at the equator. And strongest near the poles because of the difference in rotational speed. Definition. Now let us look at definition of Coriolis force. Since you know that Coriolis force is caused by the fact that our Earth, our planet, is rotating. Now let us look at the definition. It is a force that causes all surface winds to bend or curve or deviate. So Coriolis force, it causes surface winds to deflect or to deviate from its direction route. That means the wind changes its direction. Winds do not blow in a straight line from an area of high atmospheric pressure to an area of low atmospheric pressure. It deflects because of what? Because of Coriolis force. Coriolis force causes the wind to deflect. If you can have a look at this diagram, we have high pressure cell and low pressure cell. Wind is supposed to flow from high pressure to low pressure. Remember, your pressure current force is the force that is responsible for making the wind to flow from high pressure cell to low pressure cell. As you can see, it's indicated in red. This is your pressure current force, which causes the wind to flow from high pressure cell to low pressure. But now we have the Coriolis force. The Coriolis force which causes all the surface winds to deflect. If you can have a look at this, as the wind is flowing, we have the pressure current force and we have the Coriolis force, which is responsible for deflecting the wind or for making the wind to change its direction. That is why it results in this diagram, which we have here. Now the wind is taking a curved path. Instead of flowing straight from your high pressure to your low pressure area, it is taking a curved path because it's taking this curved path because the Coriolis force changes or causes the wind to deflect or deviate from its direction. So that is why the Coriolis force is responsible for that. Then the wind then take this curved path. If you have a look at this diagram, you can see the Coriolis force causes winds, all surface winds, to deflect to the right in the northern hemisphere. Winds deflect to the right in the northern hemisphere, and wind deflect to the left in the southern hemisphere. So in other words, the Coriolis force is responsible for wind deflection to the right in the northern hemisphere and is responsible for the wind deflection to the left in the southern hemisphere, as you can clearly see from this diagram. Then, lastly, we are going to discuss about geostrophic flow. We are going to discuss geostrophic flow. What is geostrophic flow? Geostrophic flow, it is an upper air wind that blows parallel to the isospheres and at right angles to the pressure gradient under the balanced forces of the pressure gradient and the Coriolis force, which means we get geostrophic flow when the pressure gradient force and the Coriolis force is balanced or is in equilibrium. That's when we get geostrophic flow. Above 600 meters, when friction is less, these winds will blow nearly parallel to the isospheres. Near the Earth's surface, friction causes winds to blow more diagonally across the isospheres. Then if we have a look at this diagram, if you can just have a look at this diagram, you can see from A, we have high pressure. And then at the top there, we have low pressure. Then the wind or the air is supposed to blow from or supposed to move from A to the low pressure at the top there. But remember, we have the Coriolis force. Then the Coriolis force causes this wind to deflect. That is why now, if you can note at B, we have the wind, it has deflected, and now it is flowing parallel to the isobars. And this is what we refer to as geostrophic flow. At B, it means that the pressure gradient force and the Coriolis force is now parallel. It's now in balance. The pressure gradient force and the Coriolis force is now in balance at B. Or we can say it is in equilibrium. That is why we have the geostrophic flow, where the air now is moving parallel to the isobars. Since you can see from this diagram, the air at A is high pressure. As it moves to C, which is a low pressure, at right angles to the isobars, it moves because of the pressure gradient force. The pressure gradient force is the one that causes the air to move from high pressure to low pressure. As soon as the air begins to move, it is affected by the Coriolis force. Then the wind the wind is deflected to the left in the southern hemisphere. Because of what? Because of the presence of Coriolis force. By the time the winds get to point B, you can see at point B, now the pressure gradient force and the Coriolis force are in balance or are in equilibrium, which means now both forces, they are equally strong. Then we have the wind is now blowing parallel to the isobars, and it's called a geostrophic wind because it has what? A constant wind direction. That is key to understand that in order to have the geostrophic flow, the pressure gradient force, the Coriolis force must be in balance. If the Coriolis force and the pressure gradient force are in balance, then we are going to have geostrophic flow. That's it for today, learners. I hope you have enjoyed the lesson. Please subscribe to my channel. I would really appreciate that. Subscribe to my channel. And if you have questions, you can ask as well. We can try to